Welcome friends, let us start our journey in this course from the state space representation of continuous linear time invariant systems. So to recap with the linear time invariant system, let us recall that a system can be represented in mathematical form in terms of differential equations, which will include the differential terms as time derivatives of the variables of the system, and such equations together represent the system, and such a representation is called a representation of the dynamical system because of the involvement of the derivative terms. If the derivative terms are not there in the representation, then it is not dynamical. Then we speak about the time invariant. So when such differential equations have constant coefficients, we say that the system does not vary with time. From time to time, the system stands in its behavior at a point in terms of the system characteristics. So it is a kind of a system which is not changing its nature from time to time. So that is called time invariant system, and it's a representation with a set of differential equations with constant coefficients. And if the system follows the linear theory of mathematics, that is superposition and homogeneity, then it forms the linear time invariant system. So we'll understand when we write the differential equations, it will be very much clear how the linear time invariant systems are represented. But in this context, it is presumed that you know about the continuous linear time invariant systems, and we are going to learn about the state space modeling of the systems. So before going for the state space modeling, let me take this privilege to define the term state of a system for you. So the state of a dynamical system is a minimal set of variables. These variables are called as the state variables. So the state of a dynamical system is a minimal set of variables such that the knowledge of these variables at time t equals to t naught together with the knowledge of the inputs for t greater than equals to t naught completely determines the behavior of the system for time t greater than t naught. Let me write this definition for you so that you are clear what exactly the state of a system means, because in the entire concept of state space representation of continuous LTI systems, we need to recollect the concept of state every time we refer to it, so it should be clear by definition in the first. So let me write the definition for you. Definition: the state of a dynamical system is a minimal set of variables, minimal set of variables known as the state variables, state variables such that the knowledge of the state variables knowledge of the state variables at time t equals to t naught, origin of time is t naught, together with the knowledge of the knowledge of the inputs for input means forcing functions so together with the knowledge of the inputs for time t greater than equal to t naught completely determines the behavior of the system for t greater than t naught. So this definition is very meaningful because dynamical system, I explained that a system with differential terms, and when the system has differential terms, when it has storage elements or delay elements, like an electrical system has capacitor, inductor, which are storage elements, that is why they are delay elements. So minimal set of variables means to represent a system, the behavior of a system at this instant of time, I need the minimum number of variables. It should not be in addition one variable or below the required number one variable. So the exact number of variables is called the minimal set of variables, and this we will define as the state variables. So at this instant of time, what I require is that I should have the knowledge of those variables at the time when I'm starting my journey of estimating or designing the system, or I am observing the system. So this is the starting time, which is I am defining as the origin of the time t naught. So I should have the information of those variables at the original time, at the time of origin t naught, and at this time what are the different forcing functions which are going to drive my system. Suppose for a car, the forcing function is the rate of the fuel input to the engine. So that is the forcing function for a car to drive the car. Similarly, to drive a DC motor, the forcing function is the voltage input. So the information about the input, that also the information should be quantitative, because if you don't know what is the magnitude of the input and what is the type of the input, you cannot take its account in designing the system or in dealing with the system. So you should know the quantitative input at a given instant of time, which is the origin of time. So from now, if I am saying that I want to see this car moving another 900 meters, so I should be knowing for 900 meters what are the values of the input at different instants of time. So together with the knowledge of the system variables and the input function to the system, we can determine the behavior of the system for all future times. So let me take an example so we'll understand it better. Let me say that I have a car. I have a car which is moving in this direction, and it started from this location, and at time t equals to t naught, at some time t equals to t1, I want to see what are the different variable values, that is the displacement, the velocity, the acceleration, what are these values I want to see. And definitely in the beginning, when I am estimating at t equals to t naught, one can say that okay, I take x equal to 0, b equal to 0, a equal to something greater than 0, because without acceleration there will not be any other changes. So I can say like that, but the case may be different. It is quite possible that we have some value of x. Suppose initially the value of x equals to 150 meters and velocity equals to some 20 meters per second, and acceleration may be some 20 meter per second square. So we have these variables associated with the system. So these variables are all the initial values, so all are x naught, v naught and a naught at time t equals to t naught. After reaching the destination or my point of estimation at t equals to t naught, so we can say that okay, a got the value 10 meter per second square, and for example I am not calculating the exact data, so a1 v1, maybe you can say that v1 has reached to some 90 meter per second, and your distance covered is some say 850 meters. So these three variables are basically the defining the system behavior of my system at the destination at time t equals to 1 is determined by these three variables. So then I have to see that what exactly I want to absorb about the system. Is these three variables sufficient to define the system's behavior at that point? If that is okay, that is all right from my requirement or perspective, then I said okay, we have a set of variables which are able to define the system behavior at any instant of time, that is x, b and a. And definitely we should know that what is the fuel discharge rate. So you may have some quantity input forcing function, so we should say that there is an input to the system which is helping us in driving the system to this position of the system behavior. So basically at t equals to t1, these three variables are defining me the exact situation of the car, and that is also called as the state of the car. So because of that, these three variables will define the state of the system, and they will be called as the state variables. Remember that the state variables are the minimal set of variables, means I don't have any more variable within the system. I don't have another variable dA by dt. This is not possible. So if you say that no, there is some other variable dA by dt, which is the rate of change of acceleration, suppose maybe p. So if it is required to determine p to know the system state at that point, so naturally these three variables will be insufficient. We have to include one more variable. So depending upon our requirement, we define the system's state variables. So these variables together form the state of a system. Now let us take a practical example so that we understand that how these state variables come into picture and how these state variables play a vital role in state space analysis of linear continuous LTI systems. So let us take the example of spring mass damper system, which is very simple example. Although in our first class we have studied that spring mass damper itself can be defined as a non-linear system, but in the context of this unit we will study the spring mass damper system as the linear system. So let us see how it works. So we take the example of spring mass damper system. So let me draw a free body diagram for your convenience. There is a rigid support with which a spring is connected rigidly, through which a rolling mass is connected, and this rolling mass is pulled by an external force in the given direction. So at any given instant there is a displacement x and there is a velocity v, and of course there is a damping. Because of the motion, we define it as with damping coefficient b. So the free body diagram would be like this. You have the mass m where some force is there in the given direction, and this spring constant is k, so some force is working against the movement and some damping force is working against the movement. So here we have the x in the given direction and the v in the given direction, and therefore we can write the equation of motion by Newton's law. So it should be the applied force at any time t is negated by the damping force, which is a function of the velocity, and then comes the spring force, which is a function of the displacement, and these all together force the system to move at an acceleration multiplied by mass. So this is the Newton's second law of motion. So let us define v, the velocity, as d of x of t by dt. So at this point let us write the equation first and equation 2 together in the form in which I am placing the displacement and removing other variable v. So we can write it in the form ft minus b dx by dt of xt minus kxt equals to capital M, then velocity is again differential of x with respect to time, so we can write it d2 by dt square of xt, and this can be written in terms of the displacement on the left hand side. So we take all the x terms on the left hand side with decreasing order of the system like this: m d2x by dt square plus b dx by d by dt of xt, then we have kxt equals to ft. So right hand side we can see there is a forcing function, and left hand side we have that variable x, which is the derivative, includes the derivative term of the displacement, and it includes basically the dynamics of the system. So all the equations, if we arrange together, we can see that at this point the state equation should be defined to go further. So these differential equations, when arranged in the form of a set of first order differential equations, are called as state equations. Let me define state equation at this point. So the differential equations, the differential equations of a continuous linear time invariant system when rearranged in the form of a set of first order differential equations define the state equation or state equations. So here in this case we understand that we have to define the differential equation or differential equations in the form of first order differential equations. That also the first order term should be on the left and rest of the terms should be on the right. There should not be any such product of the variables on the right hand side, and there should not be any complicacy of the variables like this is of second order, third order. We cannot write x square or x cube. In that case it will not be a linear LTI system. So for that, in our case, how we write the equations, let us see. So in our case we have defined that v equals to dx by dt. So here I write d by dt of xt, left hand side, right hand side vt. So vt is one variable, xt is another variable. The first order term is on the left and right side is simple variable term. Similarly I can write m d2x by dt square, which we had written early. We can write it in the form of, I recapitulate it for your convenience, m d2x by dt square, then we have b d by dt of xt, then plus k xt equals to f at t. We had written it. So we take this term, keep it on the left, and rest of the terms should be on the right. Then you replace, here I have the dx by dt term hidden, we replace it by vt. So then it becomes m d by dt of vt equals minus k xt minus b, again dx by dt term will be here, it will go to the right side, so it will become bvt, and ft is already there. So dividing both sides by m, we have d by dt of vt equals to minus k by m of xt minus b by m of vt plus 1 by m of ft. So here we have the opportunity to define these equations in terms of specific representation of the state variables. Like the first state variable, we have xt. So I define a new variable x1t, which is equal to xt. Similarly, second we have vt. So I define a new variable, I say this is x2t. And we had acceleration also, but that is the highest order, so that will be coming over here. So on the right hand side, we don't have the botheration of including the derivative term with the highest order of the variable. So we can redefine these equations as I have x1 d by dt of x1t is equal to x2t, and d by dt of x2t is equal to minus k by m x1t minus b by m x2t plus 1 by m of ft. So that is, ft is basically the forcing function or input to the system. So for our convenience, we can also replace it with the convention ut where I have defined ut equals to ft. That is just convention. So now we see that we have defined the state variables x1 and x2. So I can define it in the form of a vector representing by capital X, which includes the two variables x1t and x2t. And for convenience, we know that x1 and x2 with x small letter and subscript will be a variable over time, so I write it simply as x1 and x2. Therefore, the above representation of the state equations can be represented in the form of vectors and matrices like this. I have the x1 derivative of this by dot, x2 derivative of this time derivative is by dot, then we have minus k by m, then this is for first equation I write first. So this should be in the form of, here I write it 0 into x1 at t plus 1 into x2 at t, so it becomes 0 and 1. Similarly, here I have the coefficient minus k by m, and here I have the coefficient minus b by m. So this is a matrix, and this is again multiplied by the vector x1 and x2. So I am multiplying 0 with x1 and 1 with x2 to get x1 dot, which is same as we got above over here. But here another term is there with the forcing function, but that is associated with x2 dot, so we can write it at this, and 0 1 by m, and here you have the forcing function u. Again I am omitting the independent variable t. Now if the output is the displacement, then I represent output yt as xt, and this is equal to x1t. So well, in that case we can write yt, simply removing the independent variable t, I write y equals to variables x1, x2 multiplied by the this I should write like this is I have here y equals to 1 into x1 plus 0 into x2. So I can write it in this way, 1 comma 0 and that multiplied by x1 and x2. So that is how I can represent the state space model of a given system as shown in this representation. So this complete together represents the state space modeling of the spring mass damper system. Now this simple example can be represented through a special representation of vector, that is x equals to some matrix A into x, where this x is the differential term, so I say this is x dot, this is capital X plus b multiplied by some input u. So we generally use special representation for all the combination of these inputs as the input variables, that is the in control system we have the reference inputs, so we have r1t, r2t like that. So I represent it by r. Now y here it is single input means I am writing small I is equal to capital Y. This is equal to some matrix C multiplied by X plus another matrix D multiplied by R. So this is the representation for the state space modeling of a linear time invariant system. So let me define what are all these terms. So in our case here, this is smaller because there is only one input, and this is smaller, only one input, this is only one output, so small y, otherwise this should be capital. So we have two concepts over here, that is the vectors and the matrices. So a matrix, let me define A as a matrix, and it determines the transient behavior of the system, that is the behavior of the system at a given instant of time, which is the nature of the system, and that is independent of the forcing function. So let me define A as A11, first row, second element. In this way we go up to the n element, first row, n element. So here you come down, ith row first element, ith row second element, similarly you have ith row jth element, so you have ith row nth element. So similarly you come down, you have n elements, n1, a n2, like that you will go, so nj up to a nn. So definitely this is for a square matrix. Why this is square matrix? There is very interesting fact actually, so we'll discuss it, why it is a square matrix. So a n by n, then x is the set of state variables, so this is called the state variable itself. So we write it x1, x2 up to xn. Then comes y. So here it is single, but if there are more outputs, so naturally y will be in the form of y1, y2 up to some number, may be p outputs. And the matrix A is a matrix, of course. This is an array of rectangular array of numbers. But what about X and Y? These are actually the vectors. Any matrix with only one column is called a vector. By its very nature, we have n rows and only one column. Y has also p rows and one column. So if you study the state space model again here, you see that X is of the order of n by 1, X dot is of the order of n by 1. So this should have n number of rows because X is of the order of n, and this should have n number of columns because here X is having n number of rows, because for Hadamard product between X, A and X, that is positional product of elements summed, is called the Hadamard product of between A and n. A naturally should have the order n by n. Similarly here in case of B, you have input R, so R is again an input vector, so we can have R1, R2 up to Rn. M inputs are there, suppose. In that case, you have R of the order of m by 1, but X dot is the order of n by 1, so naturally B should be of order of n by m. Here Y is the order of p by 1, so C has p number of rows, but X has n number of columns, so naturally the order is p by n. What about D? Because R is order of m by 1, here m by 1, and Y is order of p by 1, so naturally D should be order of p by m. So to understand the concepts of the state space representation, we definitely require to learn little more about the matrix, or we should recap the concept of matrix. So with this elementary information about the state space modeling, we will define a few more terms over here, but let us recap about the matrices. So to start with, the matrix A I have defined, it is n by n matrix, but quite possible that we can have a matrix of different orders which are included at different positions in the applications. For example, this C and this D, these are not a square matrix, their order is different from a square matrix, they are basically rectangular matrices. So let us recap the matrices and vectors. So a vector, it is a column matrix that is a matrix with only one column, So we have the example of x equal to x1, x2, xn. So this is n by 1, so this is a vector. Diagonal matrix, so you all know that it has only diagonal elements a11, a22, a33, like that, ann, and other elements are 0. So this is a diagonal matrix. So identity matrix, a matrix which multiplied to any matrix in any form will be disappeared within the matrix, even to the vector. So this is of the form 1, 1, 1, like that, and other terms will be 0. Then the zero matrix, zero matrix, we will have a zero matrix represented by this, all elements 0. It can be of any order. So if you transpose a matrix A, say matrix A equals to 1 2 3 4 5 6 7 8 9, and you transpose it, so it becomes, we just write the rows in the form of column 1 2 3 4 5 6 7 8 9. So this is how the transposition of matrix can be done. Then comes your certain properties of transposition. These are A transpose, again transpose becomes A, then you have K A transpose equals to K A transpose. A transpose. This you can prove yourself. It is very easy to prove. So you have A plus B transpose, so can easily taken out A transpose plus B transpose. One very important concept in transposition of product of two matrices is that A product B whole transpose equals to B transpose dot A transpose. This you must remember. Then next comes the concept of determinants. So how do you find the determinants? These all concepts you know, but just to recap, because we will rigorously explore this concept throughout our course. So first you find the minor. So I have a determinant, say A equals to 1 2 3 4 5 6 7 8 9 10 11 12. So if you want to find the determinant of this, you have to find first two things, the minor and the cofactor. So to find the minor, you have to, if I say that you have to find the minor, say of this term, so what you do, you draw two things like this, you identify the column and the row and remove it, and what is left, that gives the minor. So we need to take the determinant for square matrices only. So here I make it 13 14 15 16. So once I remove it, so the minor of A first row second column is equal to the determinant found by 5 9 13 7 11 15 8 12 16. So let us take a simple example of finding a minor of a matrix, say A 1 2 3 4. Then there are 4 minors because we have 4 elements here. So minor 1 1 equals to, I have identified 1, so I remove this and this, so it becomes 4. So M first row second element 2, so it becomes 3. So minor of second row first element Here it is 3, so you remove the row and column, it becomes 2, so m22 it becomes 1. Now next comes the sign of the terms, so that is why we require to find the cofactors. So to find the cofactor, I just have a equals to 1 2 3 4. So again for cofactor, we find cofactor, we have cofactor for the term a11 equals to, you have m11, then minus 1 power 1 plus 1 equals to m11 equals to 4. Similarly, you have cofactor for a12 equals to row number and column number to the power of minus 1 is first row second column, and this is m12, so this is definitely equals to minus 3. Similarly, a21 should be minus 2 and a22 should be equals to 1. So from this we can find out the matrix of cofactors. So let us find out the determinant for A. So determinant for A equals to, because A is 1 2 3 4, so this determinant of A is definitely going to give us the cofactors in such a way that the C11 is multiplied by C22, then minus of 1 C12 multiplied by C22. So this expansion can be from any direction, means you can take it from the row or from the column. The basic formula we can use it, determinant of A equal to sigma j equals to 1 to n A kj c kj. So in this case I am taking along a row, so you can take it along any row. Say first row you can take it and you multiply the element with the cofactor. Similarly, you can determine in this direction also. So if you take a row, so you can make it sigma I equals to 1 to n, 1 to I equals to 1 to n A L J C L J. So this is along the row, along the column. So anyway you start expanding in one direction along any one row or along any one column, we will get the same determinant for the matrix. So similarly, you try it yourself with an example. If you don't recall already what you have learned about determinant, you can find it easily. You will recall all those things which you have learned in your 11th and 12th standards. So there is a concept of singular matrix. Most of the times we study in the context of control systems, and very much used in this syllabus is the singularity of a matrix. So a matrix is singular when its determinant is 0. So matrix A is singular if determinant of A is 0. It means a non-singular matrix can be one in whose determinant is not 0. Similarly, we have the concept of inverse of a matrix. So a matrix inverse product with A will give the identity matrix. So there are some other concepts associated with matrix, and as and when we'll require, we'll recall it, but here we are discussing only the most fundamental concepts. So another concept is the rank of a matrix. Rank of a matrix. So this you keep in mind because you will refer to this concept. So the rank of a matrix A is the dimension of the largest array of A with a non-zero determinant. So I have a matrix, suppose I have A11, A12, A13, A21, A22, A23, A31, A32 and A33. In that case, if suppose this row is 0, so naturally the rank will fall. So similarly, if the determinant of this becomes 0, so we will search for the smaller matrices if they have non-zero concept. If the smaller matrices also have the 0 determinant value, then we will say that the matrix is falling by another one rank. In this way, we keep on reducing the size of the sub matrices and find out the determinant. So the moment when we find that the determinant is not 0, we fix the rank at that point of time. So in most of the cases we have the rank of a matrix falling by 1 or 2. So this concept we will use in a later section of the syllabus, but for today this much is the concept we need to discuss, and you please recap after the class, and quizzes will be sent to you from time to time. So friends, thank you for your patient listening.